So this is the last video lecturette now, talking about the origins of the universe, and we'll just touch on it a little bit. I wish I had more time. One thing I hope to do is to add a new class over the next couple of years on basic astrophysics and talking about things like the Big Bang in more depth and detail, and talk about the origins of the universe in more depth and detail. But we're running out of time. I want to get this lecturette to you so that you can prepare for next week for all your projects to be due, your study guide 3 to be due, and to finish up the last midterm number 3 over unit 3 on the day of your last class in the week. I will post the exam right roughly 5 minutes before your class would normally start on either Wednesday or Thursday, depending on when your class is held. And you'll have 4 hours to finish the exam. Once you're done, please use, you can just give me a Word file or a PDF, but email me your results when you're done. And then don't forget to hand in your projects. That means the art and research paper and your study guide 3 is all due on the day of your exam. I hope you get these things done before that. And so it's off your back, the projects and such. So talk a little bit about the universe. Up until the early part of the 1900s, it was believed that the Milky Way was the only galaxy in the universe. That the galaxy Milky Way was the universe. I want to remind you, the universe is every bit of existence there is. There's nothing outside of that existence, is that. And so different people were studying this, and some suggested that maybe there could be something besides the Milky Way, but generally that was the consensus, that the Milky Way was the totality of the universe. There was, again, an interesting man. His name was Edwin Hubble. I'm certain you've heard that name before. At least you've heard Hubble. And he started out as a lawyer and practiced law for some years. And he frankly really did not enjoy it. And he loved astronomy. So he went back to Harvard, received a degree in astronomy, and then he began working observationally. He worked with telescopes. And luckily, he came along at the time when big telescopes were being built in America. There was an industrialist who loved astronomy, and he raised a whole lot of money to build big telescopes at observatories. And his name was Hell. George Ellery Hell. And he built the largest observatories, including he got the funding for the largest refracting telescopes. Remember, the type of telescopes astronomers now use are not lens-type telescopes. They're reflecting telescopes, or reflectors. But at the time, he built the largest lens-based or refracting telescopes. And they just have limitations. They can't get too big. They are not a good light bucket. We want big, light gathering optical elements, and lenses can't do that because their weight is just too heavy. They go out of the right shape, and therefore they don't provide the focus and the clarity of view that you would like. And because you have to keep them smaller, they don't then provide the size that you need to collect the little teeny bit of light from distant objects to be able to see them. But remember what we said when we talked about telescopes, is that mirrors can be supported from behind because the reflecting surface is on the front surface. So you can put big supports behind them and make them big. And if you get the shape of the mirror right, then they come to a good focus. If you make them large, they become a good bucket of light. and they perform everything that we want. And Hubble had the opportunity to work with these big telescopes. There were these objects in what they thought was in the Milky Way, and I'll just make it very simple looking. They had this kind of a spiral look to them. And so they were called spiral nebulae. They thought they were a part of the Milky Way, spiral nebulae. And so when Hubble used these large telescopes, what he discovered is that these are made from stars. Which is very interesting. But then he discovered a type of star that was extremely important. And that type of star is known as a Cepheid variable star. Which is a type of star that varies in brightness. And it does so in a very defined way. So if this is time for a variable star, and this is brightness for this, it makes variation going bright and then going dim and bright and dim in a very systematic way. And so these were studied. Now, in the late 1800s and into the 1900s, a very interesting woman who was very interested in science, astronomy, and physics, her name was Henrietta Leavitt, received her degrees in physics at a women's school. But unfortunately, because of the era of male-dominated science and education, she couldn't get a position at some of the more prestigious schools that would allow her to do the type of astronomy and physics that she would like to do. So she hired into Harvard and became a human computer, where a lot of women who had great mathematical skills and science skills basically were used to make calculations for the scientists and professors that were male working at these schools. And what she did, worked on the project that she was required to do, but on the time that she worked on her own time actually, she was able to study these Cepheid variables. And there's another type of variable called a RR variable, and I'll mention this in a second. And what she found is that there's a relationship between the time of going from a peak brightness to a peak brightness called the period, and how bright a star actually is. And so she developed something called the period luminosity relationship. And what that means is from the period, you get the absolute magnitude of a star. So this is the absolute magnitude. So I want to remind you, just I'll erase this up here. That remember the absolute magnitude, which is capital M subscript V, meaning visual radiation, which we talked about before. You should know these things now. Is how bright a star would be if their distance is 10 parsecs. And so always for the absolute magnitude, we assume the distance of what we're looking at and assigning their absolute magnitude is always 10 parsecs. Remember, the apparent magnitude has to do with how bright because of their true distance, little m, was the apparent magnitude. Apparent magnitude, little m, is how bright they are because of where they truly are. Absolute magnitude has to do with how bright they would be at 10 parsecs always. And what's cool, if the absolute magnitude then is a known brightness at a known distance. So we know two things here: how bright it truly is and what distance this is. And knowing this, which is really cool, if we know absolute magnitude, what's cool is we can find a star's true distance, which we call r. True distance is r. Now, I'm not going to go through the process how we do that, because it's just well beyond the scope of a class that you would find at a community college and at low level for a GE course. This is something that you would do at a much higher level. But this means that we can know exactly where these stars are found. It's related to the time it takes to go from brightness to brightness. That's known as the period. If we can measure that, and that's a simple thing, we just put an instrument that measures the brightness of this over time. And once we know that, we can determine where they are, how far from us they are. And so Hubble went ahead and did this. Just so you know, these variable stars are actually massive stars that are in the process of dying. And as they are dying, they become unstable. They're still stars, but they're dying stars, and they're off the main sequence. So we see a group of stars there called the Cepheids, which are more massive stars. Down here is less massive stars dying, are the RR Lyrae. The period for the Cepheids are quite long, weeks if not up to 100 days or so, whereas the period of RR Lyrae is only quite a bit shorter. So write that down. The period of brightness going from bright to dim to bright for these variable stars, for the Cepheid variables, is quite long, up to 100 days or so. And for the RR Lyrae variables, so the RR Lyrae variables, they have a short period. On these stars, these have a long period. But she worked with Cepheid variables. And by the way, they're called Cepheus because the very first one was observed in the constellation of Cephus. And that's the only reason why it's called a Cepheid, meaning Cephus. And that's where they saw the very first one. And so what was amazing is that when Hubble was using that very large, brand new big telescope up at Mount Wilson outside of Pasadena, he was looking at what he thought was the Andromeda Spiral Nebula, which is in the constellation of Andromeda that you can see in the fall. And looking at that, he located a Cepheid variable in there. It was like, oh, okay, that's great. So he could utilize that to determine, just how far is this in our galaxy. Now remember, at this time, the measurement of our galaxy size, which was the whole universe in their minds, was about 100,000 light years across. So let me write this down. I'll stop for a moment, make sure you have this. I'm going to lower this a little bit. You can always pause it. And I'm sorry you still have to try to read my writing. You poor people. So he found the Cepheid variable in the Andromeda, called the Andromeda Spiral Nebula. And at this point, the galaxy, which was thought to be the whole shebang, the universe at this time, the island universe of the Milky Way. Isn't that kind of romantic? The island universe was thought to be about 100,000 light years across. That's the size of the universe. Huge. 100,000 times 6 trillion miles. Hundreds of billions of stars. A huge universe, they thought. But when he used the Cepheid variable to find out how far the Andromeda Spiral Nebula was, he found it greater, the distance of the spiral, to be more than 1 million light years away. That's outside the Milky Way. And so what that means, guys, is basically he discovered the universe. He was the one that really provided the information that showed without the doubt that the universe is bigger than the Milky Way galaxy. And that the Andromeda, along with all the other spiral nebulae, are actually spiral galaxies outside the Milky Way. And so this was a massive, massive method of, or something that, a discovery that he made. His fame was right there made, but he didn't stop there. When he realized that these galaxies were not inside ours, but were separate galaxies, then he utilized something called the Doppler effect, which we've talked about. With the Doppler effect, this tells us, if a star is coming or going from us. So the relative direction of motion. And we know that coming means a blue shift, and don't know what that is, look at the videos, or going is a red shift in the spectra of these galaxies. And if you don't know what I'm talking about with Doppler effect, go back to Unit 2, because that's where I discussed this, when we talked about waves. Okay, I think it was about the last lecture on waves that we discussed this. And so first off, what he noticed is that most galaxies had a redshift. They're moving away from us, it seemed. And using the Doppler shift, just kind of like using how they find out how fast you're going in your car to give you a ticket with a radar gun. They use the Doppler shift with that. What they do is the gun shoots a radar beam towards you. Really, it's a radial beam. Hits your car, reflects back, and from that, from information from that reflected radio wave, they could tell how fast you're moving. And he could do the same thing. By using the Doppler effect and the Cepheid variable information for galaxies, he was able to see several things, meaning Hubble could see this. Hubble was the one studying this. And what he discovered is this linear relationship of how fast galaxies are moving away from us and their distance, which means there's a direct relationship of how fast they're moving away from us and their distance, which is pretty astounding. Just as a note about Henrietta Leavitt, it's kind of a sad note. She never became a professor. She should have really, in my opinion, gotten a Nobel Prize for this discovery because it is a massive discovery that she made. But instead, she continued working, and then she contracted probably some form of cancer and died at a relatively young age. Kind of a sad story. She worked with a lot of nasty chemicals, developing, images taken at telescopes. And so who knows what type of exposures she got. Again, kind of a sad story. But back to Hubble. And so what Hubble found again is that if you can do the speed in terms of kilometers, 1,000 meters per second, he would measure this in, and the distance of galaxies in megaparsecs. So a galaxy 19 million parsecs from us. Remember, parsecs, I've told you already, is 3.26 light years. So if there's a galaxy we measure to be 19 million parsecs, that's 19 megaparsecs. And what he discovered is that there's basically a linear relationship where this is the data for galaxies. And what that says, which is really cool, is when you measure the recessional speed, that's how fast they're moving apart. Recessional speed is how fast they're moving away from us. We measure that, and if we come over, we can come down and actually find their distance to the galaxy. So we can use this to find the distance of very, very far away objects. But what he imagined with this is this tells a story. And so he came from this with something called Hubble's law. And it's the basis of this graph, that the speed of recession is related to their distance, r, in megaparsecs. And so he came up with an equation. The recessional speed of galaxies is equal to a constant called h sub 0, we call it h naught, N-A-U-G-H-T, times r. And h naught is something called Hubble's constant, which is one of the most important constants of the universe. Because within this constant, it can give us detail of the age of the universe, the size of the universe, so many different things. And so it's been one of the most heavily sought number that astronomers are looking for. And so what the idea here, imagine that you're filming a stick of dynamite, say it's this, a stick of dynamite exploding. And so if you look at this stick, you got a camera, all of a sudden you would see bright light and then expansion of kind of debris and light and high temperature expanding outward. And as it expands outward, it gets dimmer and dimmer and dimmer. And the debris gets bigger and bigger and bigger. And imagine this. If we run the picture backward, we can imagine that the debris and light would come together, get brighter and hotter, and then all of a sudden come back to the stick of dynamite. So what you can imagine with this is he could imagine galaxies starting from some point and then moving outwards. And you could take that picture like a universal motion picture of galaxies moving outward, all moving away, and then you can run it backwards until finally you come at some beginning, and the beginning of that would be right there at the from the Hubble's constant. You can calculate that. So that's why we've been looking for this. How do we know that there was a beginning of the universe? The way that we know this is this way. I'll go ahead and bring this up in a second, rewrite this. If we can imagine if the universe has been here forever. So here I am, standing out on the Earth, and I'm looking at stars. Or really, I'm looking at galaxies. And no matter where the galaxies are, if the universe has been here forever, what that says is that there's enough time for all the light to finally reach me. And if that's the case, and I know how many galaxies there are, it means that wherever I look at the night sky, I should see a galaxy, which means I should see stars. And so the whole night sky should be just one bright orb made of starlight. But we don't see that. And that implies that there must have been a beginning of the universe. Because, see, if there's a beginning of the universe, yes, the nearby galaxy's light could reach me, because there's, they're close enough. But the light from very, very far galaxies wouldn't have enough time to reach me. And so we'll have darkness in between stars. And that's what we see. So if you tell your folks, you say, hey, I can prove that there was a beginning of our universe, of everything. Now, the way you do that is you walk up them out at night and say, do you see those dark spots between stars? That shows there must have been a beginning of the universe. By the way, this is known as Olber's paradox. The proof from the darkness between stars seen in the night sky that there was a beginning of the universe, which is pretty astounding if you think about it. So what we find in the universe is this, is that if we run everything backwards, you would think, just like that stick of dynamite, there would be a spot that it would start at, and then everything came out of that. And of course, one way that people say, well, every star is moving away from us, so we must have been in the center. But really, what we find is that the universe, the space, is like a balloon. So imagine that this balloon represents the space that we occupy. And glued onto the balloon are coins, and the coins represent galaxies. Now notice, the galaxies are relatively close here. Galaxies are relatively close. But what we think really was what happened is that the universe started in something called a primeval seed. And this thing was many, many times smaller than the size of an atom. And in that is tremendous energy in the form of light, no matter. Matter means atoms and particles didn't exist. And then for some reason, the universe began to expand. So this tiny thing holding energy started getting bigger and bigger and bigger and bigger. And eventually, as it got bigger and bigger and bigger, it cooled so that out of that energy, matter was formed. E, which is the energy of light, equals the mass times speed of light. So the mass that formed out of that early light of the beginning universe was equal to the energy of the light divided by c squared. So all the mass that we see around us came out of the light energy at the beginning of the universe. And so what happened? As the universe got bigger, it's like blowing up this balloon. Now, if I look at the galaxies, they're all farther apart. So if I'm sitting right there in that galaxy, if I look at galaxies, it looks like they've gotten further and further away from me than when we first started. And of course, as the universe gets bigger, this is the actual space that we walk through. Isn't that kind of weird? In other words, the space that we see around us has its structure. And even though it seems to be empty, it's still somehow getting bigger and bigger and bigger. So as the universe, represented by this blowing up balloon, gets bigger and bigger and bigger and bigger, every galaxy looks like it's getting farther away from us. So it looks like all galaxies are receding from us. and we get what's known as a redshift in their light. But if I'm on another galaxy, right here, guess what? There's close, very close. That all of a sudden they're getting bigger. All of a sudden they're getting bigger. In other words, every galaxy, no matter where you are in the universe, would see a redshift because the location of the universe where it started was everywhere because it was that tiny spot. So let me say this very clearly to you. Anywhere you would stand in the universe, on any galaxy, you would see that most galaxies are moving away from you, no matter which galaxy that you're in. And so we have some basic rules of the universe. And these are principles that we work with to try to understand what the universe is like. First off, physics works everywhere the same. That means no unicorns. We can understand it. Number two is that there's no special spot in the universe. If that's the case, that means there must be no center or no edge. Isn't that weird? Does that mean the universe goes forever and infinitely far away from us if there's no edge? We don't know. It could be that if you went out in the direction, you would never find the end, no matter if you had all the time that you would ever need. Or maybe space, which is this thing that can actually grow in size and carry galaxies with it, really, maybe as you walk out, somehow it's curved so that if you went that way, eventually you walk back to where you started from. We're trying to figure that one out. In other words, there's lots of mystery still around. And understand something. When I look at this motion of how things are, when Hubble did this graph of their speed moving away, of galaxies moving away from us at their distance, and we have that straight line, what we find is that those motions of galaxies is not because they're just moving away from us, but instead what forms that motion of galaxies moving away from us is the fact that space is carrying those galaxies with the growth of space. So space is growing. Notice that I represented galaxies by coins. The coins, they don't get bigger. So we're made from matter. So we don't get bigger or smaller depending on when the universe was. But space itself does, which is kind of bizarre. So we have these ideas. Now, do we know that this happened? This kind of all of a sudden just had this huge amount of energy flowing out? Well, imagine going back to that stick of dynamite exploding, and what happens as it expands out, if you use a camera that could measure temperature, even though it might have been a while before that, after that explosion occurred, if you take the temperature of space around where that stick of dynamite exploded, it would be a little hotter than if that explosion not happened. And so we proposed after looking at this theory, that there should be a remnant radiation in the universe, kind of like that energy that was left behind after the stick of dynamite blew off. In the 1960s, a couple of Bell Lab experimentalists using a type of telescope. It was shaped like an old-fashioned ear type of kind of a hearing aid, a horn hearing aid. I don't know if you've ever seen it in old times before they had the electronic hearing aids. They'd put a horn, and they point the horn towards you to get be able to hear you better. This was gigantic, 90 feet long or so. And as they were working with this, as they looked through space, they kept getting the signal, and they were measuring microwaves. Microwaves are smaller wavelength radio waves. I won't test you on that. But wherever they looked in space, they saw this microwave radiation, and they didn't know what it was. They thought, first off, well, maybe something's wrong with the electronics. So they messed around with electronics. They were fine. So, well, frankly, a whole bunch of pigeons had gone to the bathroom, guano inside the ear. So they thought, well, maybe that's affecting things. So they swept it and cleaned it out. That didn't affect anything. And they were talking to some physicists down the road at a university, and they said, aha. And together what they did is they made measurements, and they realized this was that echo of the Big Bang, and that radiation was everywhere. And it's called the CMB, the Cosmic Microwave Background Radiation, which is just the remnant left behind, and it's roughly, if I remember, 2.7 degrees Kelvin. Very, very cool radiation. It's cooled off over 12, 13 billion years, 14 billion years since the origins of that original expansion of the universe. But it's there everywhere. Everywhere you look, you can see it, which is pretty astounding. And so that's, and what's amazing is every way we test this theory of the Big Bang. And by the way, the Big Bang was a kind of a nasty way to talk about this theory at the origins. A lot of very powerful astronomers and physicists felt that the universe must have been here forever. It's called the steady state theory. And they hated this idea of the beginning, and they hated this theory, so they kind of snidely and sneeringly said, oh, it's a Big Bang, and that name stuck. And every way we've tested this theory, we found relative accurate results showing that that theory is right. Now, is this theory complete, meaning that has it explained everything? No, it's not. We still have a lot more to learn. And so with Hubble's law, where we have, remember, V equals Hubble's constant times R. This is V. How fast it's moving. Let me certain that this is straightforward, that you can read this. V equals Hubble's constant times the distance. Recessional velocity equals Hubble's constant times their distance to the galaxies, R. We have right now still some disagreement on what that value is, and that would change the age of the universe and would change, just other parameters about this theory. So we're still working hard on this. A lot of students ask me, Michael, do you believe in the Big Bang? And I have to keep saying, understand, science is not a feature of belief. That's talking religious issues. Science is a skeptical behavior, meaning that prove it to us. And how do we prove it? Your arguments will not prove it to us. But experiments, looking at nature based upon the theories we have, making predictions from those theories, and then testing those predictions against what nature shows us, tells us if our ideas are valid or not. And as we have tested the Big Bang theory, we've gotten the results that that really confirms that this theory is still a partial view of what took place, which is kind of bizarre. But we really believe it's there. There's only really one more thing to say. When we look at this curve, what they've realized is the actual curve is such that it's moving the expansion of the universe. How fast that universe is getting bigger, that's called the expansion of the universe, is actually faster than what we imagine it should be. So if you look over time, it's moved out faster, so it's further out in space in a given amount of time than we expect. And so what we realized is that the universe is expanding faster and faster. There's an acceleration in this expansion of the universe. So there's is accelerating in expansion of the size of the space of the universe. To do that takes energy, and we don't know what type of energy would do this. And so what we have then is we believe that there's an existence in the universe of a type of energy from that expansion that we don't know what it is, but accounts for a lot of the mass of the universe. Remember, this energy has a mass m over c squared. So every energy has an equivalent mass using this. I know the energy, divide that energy by the speed of light squared, that's an equivalent mass. And so what we say is that that energy is known as dark energy. Sounds like something from a sci-fi movie. And so if I look at the mass of the universe, everything that we see normally, we look at visible light, we know the matter that's there, the number of galaxies, all the normal stuff. So I'll call that normal mass. Only makes up about 4% of the whole mass of the universe. In other words, the more we learn, the less we know. Now we know what we know about really well. It's only 4% of what makes up everything. Dark matter, that causes galaxy to rotate faster and help the formation of the first stars, makes up roughly 30% of the universe. Wow, so dark matter makes up much more mass than normal matter we see all the time. But this is the astounding thing. Dark energy, whatever it might be, causing the universe to expand faster, is greater than 60% of the universe. Total mass, the total mass of the universe. Dark energy is much greater than any other mass. What is it? Hey, guys, tell me. I want my Nobel Prize and my $2 million. I've got a vacation. I need a vacation. But no one knows. So where are the searches in this universe? Well, there's tremendous searches. We're trying to understand the interstellar medium. We're trying to understand better the beginnings of the origins of the universe. We're trying to understand dark energy and dark matter. We have no clue. I mean, this is fun. The more we learn, the more mystery there is. And that's exciting. So we have tons and tons of things to work on as scientists and as astronomers. You know, I'll tell you, this has been a weird semester, guys, hasn't it? What a weird semester. But you're going to make it. Just keep getting the work done. Just put one foot in front of the other. And remember this. You know, when we look at the history of humankind, when we look at this, it's been one of kind of like a toddler. Toddler starts out, and they're the center of everyone's attention, and they expect that. You'll learn from them really quickly that they expect to be the center of all things. That's how humans work. We started out thinking that the universe was the center of all things. It's not true. What happened as we learned more, we went from the earth being in the center to the sun being in the center, and the sun was the center of all things, and we went around the sun. Then the more we learned, just like, oh, there's galaxies. Well, we must be in the center of the galaxy, but no, we're not. We're actually out in the boonies. Hey guys, we're the Hicks of our galaxy. Well, here I should have my piece of hay in my my mouth. We're way out here. But hey, at least we're in the only galaxy in the universe. But no, we're not. We're one of hundreds of billions of galaxies, if not trillions of galaxies. And it turns out we're even more removed from the center of all things, because remember the rule now, there's no special spot in the universe. And so that's kind of where we've been progressing. But regardless, remember, this is our world. It's the place we live. It's our life. And that's pretty dang special to us. And I hope you know it's been a pleasure to be your professor this semester. I am really sorry that we didn't have a chance to spend more time together. But we do the best we can, right? In the midst of weird things. But anyway, just keep working hard. Use this moment to challenge yourself to be more than what you could ever think you could be. Accomplish the work that you're expected to do and you expect of yourself. And let's make this time rich. And let's revel and be excited about life. And one day, all this stuff will end. And then you'll look back and think, that was a strange interlude in my life. But I'm proud of who I was. So guys, I hope you can get things done. We have lots of work left to do. Finish up your study guides. I will post today or tomorrow your spreadsheets of your grades, so look it over. If anything's missing, email it to me. I've got hundreds and hundreds of emails. I hope I didn't miss anything, or something was not deleted or somehow didn't get to me. Just send it to me. Don't freak out. I will work with you. Okay, guys, so thanks a lot for being my students. I will have office hours next week, and we'll finish out this last week of classes, and then we go into summer and see what that's like. Take care, guys. Bye-bye.